Welcome everyone to your all-in-one TensorFlow video. This is a compilation of all my single TensorFlow videos combined into one single course. It is aimed at beginners and teaches you everything you need to get started with this deep learning framework. The course consists of 11 lessons and I mixed some fun projects in between, so you will get a real hands-on learning experience that I hope you will enjoy. You can find timestamps for each section below and the code is available on GitHub. If you find this course helpful, then please hit the like button and consider subscribing to the channel. And now without further ado, let's get started. Hey guys, and welcome to my TensorFlow beginner course. In this course, I teach you all the things you need to get started with this framework, and we're going to build some nice example projects along the way. So TensorFlow is an end-to-end open source platform for machine learning and deep learning. It's developed by Google and it's one of the most popular deep learning frameworks out there. So in this first episode, I show you how to install TensorFlow on your machine. And by the way, all the course material will be available on GitHub. So I created a new repo TensorFlow course and I already uploaded the first installation guide. So you can check this out and read the guide here if you want. And now let me show you what you must do to install TensorFlow. So you go to the official site tensorflow.org and then click on install. And here you have the requirements. So you need Python 3.5 or newer, and I assume that you already have this installed on your machine. And then it's supported for Mac, Ubuntu and Windows. And the installation command is very simple. So you need pip version greater than version 19, and then you just say pip install TensorFlow. And so I show you how I do that in a couple of minutes. But first of all, let me also show you what you must do to install it on Windows and to get GPU support. So on Windows, you additionally need to install Visual Studio 2017. So you get this for free. So you only need to install the free community edition. And you also need the C++ redistributable. So you can click on this link and this will lead you to this site, and then you download the version and install this as well. And if you have this, then you can also just say pip install TensorFlow on Windows, and this works. And now if you have GPU support, then I also show you what you must do. So you can skip this part if you don't have a NVIDIA GPU on your machine anyway. So let's click on this link here, and the installation command will be the same later. But first of all, we need to have some more things. So of course you need to have a NVIDIA GPU on your machine and the necessary drivers. And if you have this, then you can install, or you have to install, the CUDA toolkit and the cuDNN tool SDK. And it's important to get the correct versions. So for CUDA toolkit, you need version 10.1. So let's click on this link. This will lead you to this site. And here you have all the archived releases. And then you select the latest 10.1 toolkit and download it for your operating system. So for Windows, and install this. And once you have installed this, you also need the cuDNN SDK. So this is the CUDA Deep Neural Network library. And on this side, you click on download. And again, here it's again important to get the correct version. So you need version 7, because right now I think the latest version is version 8. So then you click on download, and for this you need an account, so you can create this for free and then download this. And now once you downloaded this, I show you what you must do. So here I made some screenshots from my other machine where I have Windows. So first of all, after the installation of the CUDA toolkit, you probably have this somewhere on C, program files, NVIDIA GPU computing toolkit, CUDA, and then the version 10.1. This is your installation directory. And then when you downloaded the cuDNN SDK, then you can go into this downloaded folder, and there you have a bin directory, an include directory, and a lib directory. For example, in the bin directory, we have one DLL. So now you have to grab all of these files and then go back to your CUDA toolkit installation directory. And there you also have the bin, the include, and the lib directory. So you have to copy all of these files in the corresponding files in your CUDA toolkit directory. And after you've done that, you also have to modify the environment variables. So one thing you need is you need to create a variable CUDA path and then put in the installation path. And then you also have to modify the actual path variable. So in here you have to add these additional paths. So this is the installation folder with the bin folder and the libn VVP folder. So you need to put these in your path variables on Windows. And now this is all you need. So these are all the steps required on Windows. And now we can go ahead and just install our TensorFlow. So now what we do is, first I recommend to use a virtual environment, and for this I'm using Conda. So I create a new environment with Conda create, then -n, and the name I say TF for TensorFlow, and I say Python equals 3.8. And if you don't know how to use Conda, then I have a whole tutorial that explains this, so I will put the link in the description as well. And so, by the way, you don't need Conda. You can also just use the virtual env from Python. This works as well. Alright, so now we created this, and now I activate it with Conda activate TF. And now for the installation, we use pip install TensorFlow. So there is also a Conda install command available, but I actually do not recommend to use the Conda install command because this is not officially supported and there might be some performance issues. So let's just use pip install TensorFlow and hit enter. And now this might take a few seconds. Alright, so this was successful. So let's test this and see if the installation was actually successful. So let's start our Python shell. And let's import TensorFlow as TF. And now if everything worked correctly, then this should work without errors. Yeah, so this worked. We didn't see any errors. So now we have TensorFlow, and for example, we can print the version TensorFlow __ version. And we see I have the latest version 2.3.1. And then if you have the GPU support installed, you can also test this by saying physical devices equals tf.config.list.physical _ devices and then the GPU as string. And this was an error, sorry. tf.config.list _ physical devices. And here in my case, this is just an empty list, but if you have the GPU support, then it should put in your CUDA device in here. So you can test this with this command. And yeah, so for now, you know how to install TensorFlow, and I hope you enjoyed this. And if you like this, then please hit the like button and subscribe to the channel. And then I hope to see you in the next video. Bye. Hey guys, welcome to the second tutorial of the TensorFlow beginner course. Today we learn the Tensor Basics. A tensor is the central object in the TensorFlow library, so all operations are based on tensors. And a tensor is kind of like a NumPy ND array, so you can represent 1D, 2D or 3D arrays or arrays of even higher dimensions. But so let's write this down. So let's say we represent ND arrays, but a tensor is also designed so that it has GPU support. So we have GPU support. And a tensor is also designed so that we can build a so-called computational graph and then later track compute the backpropagation. So for here, for example, we multiply two tensors with each other, and then we build this so-called computational graph, and then the next operation is a subtraction. So this is also an operation in our computational graph. And then later we can use this to calculate the gradients. So it's used to build a computational graph and to compute the back propagation later. And I already have a tutorial about this in my PyTorch beginner course, but the same concepts apply here too. So if you're interested in this, then check out the video. I will put the link in the description. And then what's also important about tensors is that they are immutable. This means that we can never update the contents of a tensor. We can only create a new one. So now let's start creating some tensors. So first of all, of course, we want to import our TensorFlow library as TF. And then in order to create a tensor, we use the tf.constant function. So we say x equals tf.constant, and then we can give it a value, for example, only a single scalar value. And then let's print our tensor, and let's run this file and see how it looks like. And then we also get a warning which we shouldn't care about, so we can silence this by saying import os and then set os.environ, and then the variable is called tfcpp min log level equals, and then as a string a2. So now if we run this again, then this warning should go away. Yeah, so now we see it only printed the tensor. So this is a tensor with only one single scalar value. And we can also specify the shape by giving the shape argument. And this is a tuple. So in this case, we can say it's 1 by 1. And then we also can, for example, give it a data type. And here we can say tf.float32. So now if we run this again, then we should see the difference here. So now, yes, we also see we have the shape 1 by 1. So now it's not only a scalar value, but a matrix. And we have a different data type. This is with only a single value. Of course, we can also put in a list in here, so we can say, for example, 1 and 2 and 3, and now we have a 1D tensor. So here we see the shape is 3, and in this case we say this is a so-called rank 1 tensor. And of course we can also put in a list of lists. So let's create another list, and the first one is this one, and now let's create another list. And this has the values 4, 5, and 6. And now in this case, this is a rank 2 tensor. So now let's print this again and let's have a look at the shape. So here we see our tensor, and we see the shape is 2 by 3. So this means we have 2 rows and 3 columns. So now in this case, we created the values manually, but there are also some methods to fill our tensor with some values. For example, we can say our tensor is tf.width ones, and then we can give it the shape as tuple, so let's say 3 by 3. And this is a 3 by 3 tensor filled only with ones. So here we have it, and we see that the default data type here is the float 32 if we don't specify any. So similar to ones, we can also use zeros. This will do the same thing, except that it fills our tensor with zeros. So here we see our 0 tensor. Then there's also a method that is called tf.I, and this only takes a single value. So in this case, let's put in a 3. So this will create the identity matrix, where the diagonal matrix or the diagonal is filled with ones and the rest is filled with zeros. So this is the I function. Then there are also methods to initialize our tensor with random values. So for this we can, for example, say tf.random and then draw some values from the normal distribution. So normal, and then here again we need the shape, so let's use 3 by 3. And here we can specify the mean, so by default this is 0, and the standard deviation by default is 1. So let's print our random tensor. So here we can see the random values, which are somewhere around 0. And we can also, instead of the normal distribution, we can draw values from the uniform distribution by saying tf.random.uniform. And then again, we need the shape. And here we can specify the min val. So let's say this equals 0 and the max val equals 1. So this means all of our values are between 0 and 1, and they are uniformly distributed. So here we have our new random tensor. So now we can also use the tf.range function. This is similar to the normal Python range function. So now we have values between 0 and 9. Oh, of course I have to print it. So let's clear this and run this again. So yeah, this is our range tensor, and now let's see, by default, in this case, this is data type int32. So let's say we want to change this, so we want to cast our tensor, and we can do this by saying x equals tf.cast, and then again the tensor we want to cast, and then the data type equals, let's use tf.float 32, and let's print our new tensor. And again, notice that I assign it again to the new value because the original tensor is immutable. So let's run this. And then we see we get the same tensor, but now with a different data type. So this is how we can cast tensors. And now let's talk about operations on tensors. And what is important here is that all operations are element-wise. So let's create two tensors, x equals tf.constant and then a list 1, 2, 3. And let's use the same with a new tensor y, and it gets the values 4, 5, 6. So now, for example, we can do a element-wise addition by saying we have a new tensor c equals, and then we can use tf.add x and y. And now if we print our c, then let's clear this and run this. Oh, here I have a typo, constant of course. So again, let's clear this and run this. Then we see here's our new tensor 5, 7, and 9, and this is because we did 1 plus 4 equals 5, 2 plus 5 equals 7, and 3 plus 6 equals 9. So all the operations are executed element-wise, so this is important here. So instead of using this add function, we can also just use c equals x plus y. So this is doing the same thing. So now if we print this, then we should see the same result. Then instead of the addition, we can also use subtraction by calling tf.subtract or just saying x minus y. So again, this is doing the same thing. Then we can do element-wise division by saying tf.divide, or again, we can just use this operator here to divide our tensor. Then we can do element-wise multiplication by calling tf.multiply, or again use the star operator. Then we can compute the dot product by calling tf.tensor dot and then x and y, and here we have to specify the axis equals 1 in this case. So let's clear this and run this, and now I have to remove this, of course. So let's run this again. So this is producing a single value. So what we are doing here is we compute the product of these values and then sum over all values. So 1 times 4 plus 2 times 5 plus 3 times 6. So this is a single value. Then we can do a element-wise exponential product with the double asterisk operator. So we can say c equals x star star 3, for example. So let's run this. So here we get 1 times 1 times 1 equals 1, 2 times 2 times 2 equals 8, and 3 to the power of 3 is 27. So this is the element-wise exponential product. Then let's do matrix multiplication. So for this, let's create 2 new tensors with the random function. So in this case, let's use random normal and the shape 2 by 2, and let's use the same for our y. And then to do element-wise matrix multiplication, we can say c equals tf.matmul and then x and y. And let's print this again. And then here we see we get the matrix multiplication result. And in this case, we must be careful. So here the shapes must match. So the number of the columns of our first tensor must match the number of the rows of our second vector. So this dimension, for example, if we use a 3 here, must also match this dimension. So here we can use a 3 by 4, for example. The only thing that is important is that these two numbers here match. So now let's run this again and see if this is working. So yeah, here we have a result, and the resulting shape is 2 by 4. So these two numbers stay basically. So this is matrix multiplication, and we can also overload this with the add symbol. So we can say x add y, and this is doing the same thing. Then let's talk about slicing and indexing. So this is the same with NumPy arrays or Python lists. So we can access them in different ways. So let's create a constant tensor with 2 dimensions. So a list of lists, let's say 1, 2, 3, and 4, and another list 5, 6, 7, 8. And now, for example, we want to access only the first row. So we get this by saying x and then the index 0. So let's clear this and run this. And then we see we only get 1, 2, 3, and 4. Then we can also use a colon here and then a comma. So this means in the first dimension we want everything. So we want all the rows but only column 0. So let's print this. And we see we get 1 and 5. And we can also do it the other way around. So we can say only column only row 0 and all the columns. So this is basically the same if we are only using a 0 here. Then we should get 1, 2, 3, and 4. So yeah, here we have the result. And again, here we can specify the start and stop index. So by default, it's going from all the way from the start to the end. But of course, we can also specify the start. So let's say 1 and let's say 3. So the last one is not included. So now this is only using index 1 and index 2. So we should get only 2 and 3. So yeah, this worked. So here we get only 2 and 3. And now if we put in 2 single values in here, then we access a specific element. So here, let's say we are in row 0 and we want column 1. So this should be the value 2. So let's print this. All right, so here we see value 2. So this worked. So this is how we can apply indexing and slicing. And now let's talk about reshaping of tensors. So again, let's create a random tensor with, let's say, tf.random.uniform, or let's use the normal distribution, and the shape should be 2 by 3. So let's print our x first. So let's clear this and run this. Then we see our shape is 2 by 3. So let's reshape our tensor. So we can say our new x should be tf.reshape, and then the original tensor is again our x, and then the new shape is 3 by 2 in this case. And let's print our x. And then this should work. Oh, I forgot the x here. So again, let's run this. And of course, we can only use shapes here that are matching, so that can be applied out of these original shapes. So in this case, it worked. We can also, for example, just use a single shape with 6 values. So 2 times 3 equals 6. This is why 6 is working as well here. So now we have a tensor with the shape 6, so only a 1D array. And you can also use a -1 here. For example, if we say a -1 and then a 2, then it will automatically determine the correct shape for you. So in this case, this should be a 3 by 2 again. So here we see the shape 3 by 2, so this worked. So yeah, and as I said in the beginning, a tensor is kind of like a NumPy array, so you can convert a tensor to a NumPy array and vice versa. So let's see how we can convert to a NumPy array, and this is very easy. So you just say our x, or let's say in this case, let's use x equals x and then call the NumPy function. So now if we print our x, then it should look the same. And if we print the type of x, then we should see that this is indeed a NumPy array. So let's run this. So yeah, we see our x has the same values as the tensor, but now we see it is a NumPy array. And to convert it back, we can say x equals tf.convert and then underscore to tensor. And then again, we put in the NumPy array. And now if we print the type of this one, print type of x again, then we should see this should again be a tensor. So yeah, this worked. And so we see this is a TensorFlow eager tensor, and you shouldn't worry about this now. So what eager tensor means is that it evaluates the operations immediately without building this computational graph that I mentioned in the beginning. So, but yeah, as I said, you shouldn't worry about this now. Just know that this is a tensor. And this is not only because I used this convert to tensor functions. So all of these constant values. So if I use tf.randomNormal or if I use tf.constant and then a value here. So all of these are eager tensors. So here again, we see a eager tensor for this one as well. So yeah, these are all the functions that I wanted to show you. And now a couple more things that I want to mention. So instead of using numbers here, we can also, for example, use a string and get a string tensor. So let's print our new string tensor and let's clear this and run this. So here we see we get a tensor with the data type string, and again here we can use a list and produce a 1D string tensor. So for example, we can use another name and another name, Max and Mary, and now if we run this, then we see we have a string tensor with a different shape with multiple values. So this is working as well. And then one more thing that I want to mention. So here, as I said, we used constant tensors, so they are immutable. But there is also a different kind of tensor, and this is a TensorFlow variable. So instead of using, for example, let's use 1, 2, and 3 with this constant function, we can do the same thing with tf dot with a capital V and then variable. And now if we print this, so now we see it looks the same, but we also get the hint that this is a TensorFlow variable. And a variable should be used when you want to modify its value. So for example, a TensorFlow variable is used to store the model parameters that we are then updating during training. But you don't need to worry about this now because we are going to use a higher level API, and this is the Keras API. And this is doing all of this stuff for us, so we don't need to worry about using a variable and then updating the weights. So, but you should know that this exists, and this is different than a TensorFlow constant. And yeah, I think that's all I wanted to show you about the tensors, and I hope that you enjoyed this tutorial. If you enjoyed it, then please hit the like button and consider subscribing to the channel, and I hope to see you in the next video. Bye. Hey guys, welcome to the third TensorFlow tutorial. Today we're going to build our first neural network. I will not explain the theory here and instead focus on the implementation, but I will provide some links in the description if you want to learn more about this. And I will also provide the slides as well as the code in my GitHub repo. So we implement a neural network that will look like this. Our neural network has multiple layers and it gets an input image and then it processes this image, and at the end it produces a probability for each class. So we have a multi-class classification problem here, and this means that at the end we use a softmax layer to get the probabilities. So this is what we're going to code, and I promise that the final code will look relatively easy because TensorFlow takes care of a lot of things for us. So even beginners should be able to build a neural network like this. And TensorFlow provides two different kind of APIs, the Keras sequential API and the subclassing API. The Keras API abstracts away a lot of things and makes implementing the algorithms much easier. So they say here that this one is for beginners and the other one is for experts. But I don't think that this is a good description because I think that Keras is good not just for beginners, but it's also a good fit for experienced programmers. So this is a great API here and you can implement a lot of things. And then only when you need more flexibility, you can or should switch over to the subclassing API. So in this beginner course, we concentrate on the Keras sequential API, but I will also cover the subclassing API in later episodes. So for now, let's use the sequential API and let's jump to the code. So I already imported TensorFlow and I silenced some warnings like in the last episode, so you don't need to worry about this. And now let's start implementing our network with the Keras API. So we also say from TensorFlow we want to import Keras. And since TensorFlow 2, this is included. So before it was a separate API, but now it is fully integrated. So then we also import NumPy as NP, and we import matplotlib.pyplot as plt because I want to show you a plot. And now let's get our data set first. And in this tutorial, we use the MNIST dataset, so the famous dataset for handwritten digit classification, and this is included in keras.datasets.mnist. And then we get training and testing sets by saying xtrain and ytrain, and then comma, and then another tuple, and then xtest and ytest. And this is mnist.load data. So we have to use two tuples here because this is what the load data returns. And then, for example, let's print xtrain.shape. And let's also print ytrain.shape. So now let's open our terminal, and here I'm already inside the virtual environment with TensorFlow installed. So let's run this file. So this is this file here, and let's have a look at the shape. So we see our xtrain has this shape, so we have 60,000 training images, and each image has the size 28 by 28, and then we have 60,000 labels corresponding to the data here. And by the way, this is a NumPy ND array right now, so this is not a TensorFlow tensor, but we can still use it for our model then. So the first thing I want to do is I want to normalize the data, because right now the images have values between 0 and 255, and we want to normalize this so that the values are between 0 and 1. So we say xtrain and xtest equals, and then we say xtrain divided by 255 as float, and the second one xtest divided by 255. So we can do this in one line for both data sets. And now let me copy and paste some code in here. So I want to plot the data. So we just say plt imshow to plot 6 different images, so the first 6 digits. So let's run this and have a look at the plot. All right, so this is what the plot looks like. So here we see the handwritten digits, so very simple, and this is what we're going to classify. So let's remove this and let's build our model. So let's build our model, and as I said, we're using the sequential API. So we set model equals, and this is a keras.model.sequential, and here we pass in a list with all the different layers. So similar like here, we want to have different fully connected layers. So let's start with keras.layers.flatten. So this just flattens our image to reduce one dimension of this 28 times 28. And then we are going to use our first real fully connected layer. So we say keras.layers.dense. So the dense layer is the fully connected layer in the Keras API. And here we have to specify the output. So this is a hidden size that we can specify. So I'm going to use 128 but you can use a different one here. And then we also say activation equals ReLU. So we're going to use the ReLU activation function. So if you have a look again at this plot, then usually all these layers are followed by activation functions. So I have a full tutorial about activation functions in the PyTorch beginner course, but the same concept applies here too. So I will put the link in the description and you can check it out. But basically what you should know is that it introduces non-linearity and it improves the training. So it makes our model better. So we should use a activation function after each of these layers. And then, so let's use just one in the middle, and then let's use our final layer. So this is again a dense layer. And now we need to specify 10 outputs. So we do have 10 different classes. And for each class, we need one output. So in this simple example, we only have 2 different classes, dog and cat, and that's why we only need 2 output layers. But in our example, we have 10 classes, so that's why this must be 10. So this has to be 10, but you can play around with this size. And then, as I said, we want to get the probabilities, so that's why we need a softmax layer. So we could include this here by saying keras.layers.softmax. But actually in the TensorFlow docs, they say that this is not recommended, but instead you should include it in your loss function later. So we leave this out for now. So now this is all that we need for our model, and our model can automatically determine the correct input sizes. We only need to specify the output sizes. But let's say after we create this, we want to call model.summary and we want to print this. So right now this doesn't work, but if we specify the first input size, so here we can say input shape equals and then 28 by 28, then this works. But you don't have to do this. It can also figure this out when you fit it to the training data later, but then you can only print this after you compiled your model. So it's a good practice to include this here. So now let's save this and run this again, and then we will print the model summary. And here I forgot to include an S, so it's called keras.models.sequential. All right, so here this is the printed summary. So it prints all the different layers. So here we see our first flattening layer, and this has the shape 784. So this is 28 times 28. It reduces it to 1 dimension. And this is not an actual layer that we have to train, so it doesn't have parameters. Then we have our first dense layer with 128 output shape. And this is the number of parameters, and then our second dense layer with 10 outputs. And here the first one is just none, so this is the number of samples that we don't know yet. And then we also see the total params and the trainable params. So yeah, so now we already have our model. And by the way, so I think you can already see how simple it is with this sequential API. And there's also a second way to do it with this sequential API. So you can set up your model like this and then add each layer separately. So you can call model.add and then you use this layer, and then you say model.add and then you use this layer. Model.add add and the second layer, and then model.add and the last layer. So this is doing the same thing, but this is the advantage that now you could print model summary after each operation and figure out how your training looks. So yeah, keep that in mind that you can do it like this as well. So we're just going to use the first one and comment this out again. So now we have our model, and now the next thing we need is the loss and optimizer. So in a multi-class classification problem, typically we use the categorical cross entropy. So we say loss equals, and then we say keras.losses, and then here this is actually called sparse categorical cross entropy. And this is because our y is an integer class label. So it's 0, 1, 2, 3, or something like that. And that's why we use this. Sometimes the label is also encoded as 1 hot. So a 1 for the class 0 and then 9 zeros for the other classes. So in this case, we just use the categorical cross entropy, but in our case, we use this one. And we also say from logits equals true. And this is because here at the end, we didn't include the softmax. So we still have the raw numbers, the raw logits. So we have to use this, otherwise it won't train very well. And then we need to create an optimizer. So we say keras.optimizers, and then here let's use the Adam optimizer, a very popular optimizer. And we need to give it a learning rate. So we say this is 0.001. So this is the one of the most important so-called hyperparameters that you should tweak in the beginning to get a good result. So play around with this. And then we also define some metrics that we want to track. So in this case, this should be a list. And here we only want to track the accuracy metric. So when we have this, then we call model.compile. So this is what we do with the TensorFlow framework. And then we say our loss equals the loss, our optimizer equals the optimizer, and the metrics equals the metrics. So this will configure the model for training. And after that, we can start the training. So let's define the batch size and set this to 64 and set the number of epochs for our training. So here I only use 5 epochs. And then we can simply call model.fit, and we want to fit the X train and the Y train, so our training data. And we specify the batch size equals the batch size, and the epochs equals the epochs. And then we set shuffle equals true. So this is the default, but I want to stress this, that you should always do this during training. And then let's set verbose equals 2. So this is just for logging. 0 means no output, 1 means a progress bar, and 2 means normal logging. So this is all that we have to do to train our model. So again, we build our model with the sequential API. Then we define the loss and the optimizer and optional some metrics. So we don't have to use this here, but we can. And then start the training with model.fit. And now we can already start training this. So let's run this. So now we see that it's starting the training, and after each epoch it prints some metrics. So it prints the loss and the accuracy because we specified this. And we see that after 5 epochs we already have a very low loss, so this decreased, and our accuracy is 98%. So our simple neural network is already very good for this task. So now that we trained it, what we want to do then is want to evaluate our model, and we can also very simply do this by saying model.evaluate, and then we use our test data. So we use X test and Y test. And again, here we can use the batch size and set this to our batch size. And I also set verbose equals 2 for some logging. So this is how we evaluate it. And so the batch size means that it takes some batches and performs the computations on the batches. So this can make the training and evaluation faster and also improve the training. So let's run this again. So for now I didn't save the model, so now I have to train it again and then evaluate it. So let's run it, and in later episodes we learn how we save our model after the training. Alright, so training is done. So again, we see the 5 different epochs, and then we have one print statement for the evaluation. So we see that it's slightly lowered the accuracy for the test set, but it's still very good. So now we already have a very good training to classify the MNIST digits. And now let's see how we can do some predictions with our model. So there we have several different options, and again, for the predictions we need the softmax layer to call the probabilities. So we didn't put this in here as the last layer, but it was automatically included here during the training. But now we need it, so our first option is to create a new model. So let's call this probability model, and this is also a keras.models.sequential model. And here, this is one new thing that I want to show you. We can pass a whole model into this, so we can put in our original model. So now it has all of the layers of this model, and now we use the keras.layers.softmax layer, and now that we have this, we can call this probability model. So we say predictions equals probability model, and then pass in the X test data. So now we have this, so we can, for example, get the first prediction by saying this is the predictions index 0. And let's print this here. So print prediction 0. And then this is the probability. So now we want to choose the class with the highest probability. So we can do this by calling the argmax function. So we say label 0 equals numpy.argmax, and then of this prediction pred 0, and then print the label 0. So now let's save this, and now I run the training and evaluation again, and then print this for you. Alright, so it's done, and here it prints the prediction 0. So for each class it has a probability, and then we take the label or the index with the highest probability. So this is index 7 in this case. So I think it's this one. So 9.49, this is the highest one. So yeah, this works. So this is the first way to do it. The second way is to use our original model plus the softmax separately. So we can say the same as we are doing here, predictions equals, and then we call the original model and pass in x test. And then we apply the softmax for ourselves. So we say predictions equals TensorFlow.nn.softmax. And then here we put in the predictions. And now we have the same as we have here. So let's print this one. And then when we run this and print this, then we should see the exact same numbers. Oh, sorry, I stopped this for now. So here I forgot to get the prediction 0 so that we see this is the same here. So let's clear this and run it again. All right, so again, our training is done, and here you can see that it prints the exact same numbers and the same class label. So you can do it like this. And then as a third option, instead of calling model model like this, you can also call model.predict and then the data. And here you can also specify the batch size equals the batch size. So then it computes it for each batch. So this is also what you can do. And again, the numbers should be the same. And now let's not only get one single prediction. So let's say we have 2 or 5 different predictions. So let's call this 0, 5s. And then we get this by saying predictions and use slicing from index 0 to index 5. And now let's print the pred05s.shape first for you. And now if we call the argmax for this, so now let's say our label 0,5s equals, and then if we get the predictions, if we call the numpy.argmax with this 5 predictions, then we also have to specify the axis, and in this case we want to compute it along axis 1. And now we should get 5 different labels, so print label 5 zeros. And now let's clear this and run it one more time and hope that this works. All right, so again, this is done. We see that again with this model predict, we get the same numbers. And then this is our shape, so 5 by 10, so 5 different samples and or predictions. And for each prediction, 10 different probabilities like here. And if we call the argmax along axis 1, then we get 5 different labels. So again, the first label is label 7, like here. And these are the next predictions. Yeah, so this is how you can predict it. And I think this is all you should know to build your first neural network. So again, you build your sequential model, then you set up loss and optimizer, then you compile the model, then you call model fit and model evaluate. And then when you want to predict, you can call model predict. But yeah, don't forget to call the softmax if you want the actual probabilities. And yeah, I think that's all for now. And I hope you enjoyed this tutorial. Please hit the like button and consider subscribing to the channel. And I hope to see you in the next video. Bye. Hey guys, welcome to the next TensorFlow tutorial. In the last video, we learned how to create a neural network and then train and evaluate the model and make predictions. And now in this tutorial, we implement our first real-world project. So we deal with a regression problem and we learn how we load the data, analyze the data, and apply some pre-processing. And yeah, as I said last time, we already used a deep neural network. And here we first take a step back and apply only a linear regression model, so only one layer. But at the end we extend this to, again, a deep neural network. And with this you should get a better understanding of the Keras dense layer and also of actuation functions. So here I'm in a Jupyter notebook and you don't need to worry about this. This just makes life a little bit easier for me to explain the code to you and show you the different steps. But you can code all of this in a normal Python file. So let's start, and first we import the things we need. So again, here I silence some warnings. Then we import matplotlib NumPy, and then this is new. So now we use pandas, and you can install this with pip install pandas. So this makes it very easy to work with data sets and analyze them and modify them. And then here I set some print options to make the outputs a little bit nicer. And then we import the things from TensorFlow. So again, we import TensorFlow STF. Then we import Keras. So the last time I told you about the Keras API, and we already used the Keras layers. And now this is new. So we also import from TensorFlow Keras layers.experimental. We import pre-processing to apply a pre-processing layer to our data. So these are the imports we need. And now for the data set, so we are going to use this auto MPG data set. So this is a data set from the year 1983. And here we have different features. And with this, we predict the MPG for a car. So how many miles a car can travel using 1 gallon of fuel. And so here, this is a very popular website where you find a lot of machine learning data sets. And now if you click on the data folder, then here you get the link to the actual data. So now here in the Jupyter notebook, this is the exact same URL. And I already wrote the different column names up here. And then with pandas, we can say pandas.readCSV. So the ending here is not .csv, but it's still in the CSV format. So we can use this. And you can also use this method if you have a CSV file on your disk. So this works as well. So now let's load our data, and then we can call dataset.tail. So this prints the last 5 columns. So here we see the MPG value that we want to predict and the different features. So for example, we have the number of cylinders, the displacement, the horsepower, the weight, acceleration, model year, and origin. So yeah, this is our data set, and now we clean our data set. So in here we have some missing numbers, and we can very simply exclude them by saying dataset.dropNA. And then we also change this last column here because this is actually a categorical value and all of the other ones are numerical values. So this might confuse our model. So we want to change this in a one hot encoded data. So we can call dataset.pop origin to remove this. And here in the origin, we have the different countries, USA, Europe, and Japan. So we can add them like this. So now again, if we have a look at our tail, then we see we removed the origin value and instead included one hot labels. So here for label 1, it's the USA. For label 2, it's Europe. Then again, label 1, so again, USA has the 1, and so on. So now we have this, and now we want to split our data into training and test set. And we can do this by calling .sample and then use a fraction here. So we use 80% for training. And we again drop these samples. So all of these samples, all of that we specify here are not included in the test set. And then, yeah, let's print the shape, and let's also describe our data set. So we can very easily do this with pandas as well by calling the .describe function. And then here we see we have our whole data set has 392 samples and then 10 different columns for now. And then our test data, our training data is 80%, so 314, and the rest is for testing. And now if we call the describe function, then it analyzes some statistics like the number of samples, the mean, the standard deviation, the min and max. So this might be useful to analyze it. And first of all, now what we want to do is we want to split the features from the labels. So we want to, this is our label that we predict, MPG. So first we make a copy. So we say these are our train features and our test features. And then we simply pop the MPG column from the training and testing data. And when we pop this, then this also returns the data. So this is now our training and testing labels. So now we have this. Then here's a simple function to plot the data with matplotlib. And now let's simply plot one feature. So let's plot the horsepower feature. And we plot this against the MPG value. So we see the more horsepower our car has, also the less is the value of MPG. And this makes sense because the more power our gas has, the more fuel it needs. So the less is the MPG. And so then we also, let's plot the weight feature, and this should have a similar distribution. So again, the higher the weight of a car, the more fuel uses it, and the less is the number of the MPG value. So yeah, so this is how our data looks like. And now if we go back to the describe function and have a look at the different mean values, then we see these all have different ranges. And this is again a very important issue that we have to consider. So these different ranges, if we leave it like this, then it might confuse our model. So it's recommended to normalize the data first. And to normalize, so let's print, again, let's describe our training data set and but let's print only the mean and the standard deviation. So if we run this again, then here we see the different means. And now to normalize it, we use this normalization layer from the pre-processing module. So this one here that we imported. So let's code this. So here we create a normalization layer. So we say normalizer equals pre-processing dot normalization. So this is a Keras layer for the sequential API. And to call this, we have to adapt it to the data. So here we say normalizer.adapt, and then we want to adapt it to the training features. And right now this is a pandas data set, so we can convert this to a NumPy array and then call the train features. So what this is doing for now, this simply calculates the mean and the variance of this training features and then stores them in the layers. So now, for example, we can say print and then normalizer.mean.numpy. And then if we run this, then we see here these are our mean values. And these are the exact same numbers as we see here if we go this first column down. So this simply stores it. And now whenever we apply this layer to our data, then it normalizes the features such that it computes this formula. So it subtracts the mean and then divides by the standard deviation. And this means that our output has a 0 mean and unit variance. So here, let's get some example. So the first data from the training features. Then let's print this one. So this is the first data, unnormalized. And then we also want to print the normalized one. So let's print normalized. And then here we have to call this layer normalizer with our data. So first, and then convert it to NumPy. So this is how we convert from a TensorFlow tensor to a NumPy array. So let's run this. And then we see we have the first layer with different scales and ranges. And now our normalized data, so they are all somewhere around 0 with a unit standard deviation. So this is how we apply a normalizer pre-processing layer. And now let's tackle our regression problem. So in regression, we have this distribution that we know from the training data. And now when we get a new data, we want to, so for example, here we get a new weight sample, and then we want to predict how much MPG we have for this car. And for this, we fit a function, so a linear function with this formula, so we can approximate it with m times x plus b. So this is basically a line equation. And we use this with the layers, with the dense layer. So to better understand this, now first, let's not use all of the different training features that we have. So all of these. So let's just use one so that we can stay in the 2D case. So in this case, for example, let's use the horsepower. So here, let's define our feature, and this should be the horsepower label. So I will implement it like this, so then you can just change the feature here, and then you can try out different features. So you can also, for example, use weight here. So all of these names you can use here as a feature. And now let's get the single feature or the single data. So let's call this single feature equals NumPy array. And then from our training features, and then we can access it with the feature. This will only return the horsepower feature. So let's print this. Let's print single feature.shape, and let's print train features.shape. So now if we run this, here I have a typo array. Let's run it again. Then we see our single feature only has one feature, and in the whole training data we have 9 different features. So then up here we created this pre-processing or normalization layer and then adapted it to all of the features. So basically we have to do the same thing, but now adapt it only to the horsepower feature. So let's call this single feature normalizer. Then again, our single feature normalizer, we call the adapt data and adapt it to the single feature, single_feature. So now we have this and can run this code. And here I have one parenthesis too much. So again, so now we have this single feature, and now we create our sequential model as the last time. So this is very easy with the Keras API. So we say our single feature model equals, and then we say keras.models.sequential. And then here we use a list with all the different layers. So we use this as a first layer. So the single feature normalizer. And then we only use one layer, so one dense layer, and the output, or also called units, number of units, is only 1. So this is all that we need to build a linear regression model. So this is a linear regression or linear model that applies exactly this formula. So it has some weights and multiplies it with our input, and it also has a bias. So this is all that we are doing here. So let's run this and let's print the model summary. And then we see we have our normalization layer and our dense layer and only 5 parameters. So it's very simple. And now as a next step, the same as last time, we define a loss and a optimizer. So for the loss, we use keras.losses, and in the case of a linear regression, we can use the mean absolute error. So this is one possibility. We could also use the mean squared error, so you can try out both. And so this is simply this one is doing the prediction y prediction minus the actual y, and then the absolute value, and then sum it up over all samples and calculate the mean value. And the mean squared error is the same, except that it's using the square here and not the absolute value. So yeah, try that out for yourself. And now the optimizer equals, so the same as last time, keras.optimizers. Let's use the Adam optimizer, and we have to give it a learning rate. Let's try out 0.1. And then after we have this, then we compile our model. So single feature model.compile. And here we give it the optimizer equals the optimizer and the loss equals the loss. And yeah, last time we also gave it the metrics that we want to track, so the accuracy, but the accuracy doesn't make sense here for the regression, so we leave it away and then we simply see the loss later. So let's run this. And now to train the model, we simply have to call model.fit like the last time with our training features. And here we only want the single feature that we define, so the horsepower in this case. But we still include all the training labels. Then we define the epochs. Then here I set verbose to 1 to see some logging. And we can also define a validation split. So this automatically takes 20% of the training data and then uses it for the validation data to tweak the hyperparameter. So let's train our model. And now training is done. And now we see that the loss decreased and we also see the validation loss decreasing. And at the end, we have a training loss of 3.8 and a validation loss of slightly more, 4.1. So it's not very bad. And by the way, if we call model fit, then this returns the history where it stores both of these losses. So we can assign it to a variable, which I called history here. And then I simply plot the history. So then we can access these two losses by calling history.history and then access the loss and the validation loss. So let's plot this. And then we see that our losses decreased. So it looks very good here. And then to evaluate our model, we simply, like last time, call model.evaluate with our test features, only with horsepower and the test labels. So let's run this, and this was very fast. So here we see we have a final loss for the test data of 3.6. So not very bad. And now let's predict some samples. So in this case, I simply create test data, so all the values between the min value and the max value, and increase the range a little bit. You could also just use a hard-coded number here, like from 0 to 250, but I want to be it like a little bit more suited for the used feature. So we use this, and then to predict, we call model.predict, and then our new test data that we want to predict. And then we plot it with our function from the beginning. And this is the same plot as in the beginning. So we plot the horsepower against the MPG value. And then these are our new X values that we predict. And we see that our prediction, so here we plot a line, and this is a linear line since we use a linear regression model. And we see that it's not too bad. So we see the same trend. So the more horsepower our car has, the lower the MPG is. But for example, here in this area, it's staying the same, except that our horsepower is further increasing. So yeah, in this area and also maybe in this area it's not perfect. So, but in the rest it looks okay. So yeah, so this is how we apply a linear model. And again, we only need the one dense layer with one output unit, and we also applied this normalization layer. So this is all we need to use linear regression. And now let's extend this to a deep neural network. So as I said, with only one dense layer, we can only only get a linear linear function here like this, which is not perfect. So to further improve this, we can introduce more layers here and convert this to a fully feed-forward neural net. So we still use the normalization layer and the dense layer at the end, but in the middle we use some more dense layers. So let's say layers.dense, and then here you can try out different values for the hidden size. And as I said in the last time, we also apply activation functions for these layers in the middle. So let's use the ReLU again like last time, and then let's use the same one again. And yeah, and then at the end we use our dense layer with one output. And now this is all we need. And now we converted our linear regression model to a deep neural network model. So let's use this. And then again, we compile it with the loss and again a Adam optimizer, and call the summary to see the different layers again. And then we see there is a lot more parameters that we have to train now. So now again, let's call model fit with our horsepower feature and start the training. And training is done, and we see the final model or final loss is slightly better now, so slightly lower than before. So let's evaluate our model. And now it's below 3, so it's definitely better. And now again, let's make some predictions and plot this. And now we see a new plot, and now we see that our function is no longer only linear, but here we also have some nonlinear areas. And this is the effect of the activation functions that we used. And that's why this is such an important thing in neural networks, to apply activation functions. So here again, we have this only our linear regression model with one dense layer. So here we can only predict a linear function. And now with a deep neural network, we can get a nonlinear function as prediction. So yeah, I think that's all. And now, so we only used one feature for now so that we can stay in this 2D case. But of course, we can include all of the features, and we do it the same, so we don't have to change anything actually. So we use this normalizer that we adapted to all the training features. And here we have only our single dense layer. Then we compile this, and then we fit it here to all of the training features and train it. And now training is done. And we see that the loss is also below 3. So training on all features makes it further better. And now let's evaluate it as last thing, and then we see we get the final loss. So yeah, so you see the code is actually the same. We just use all of the training features here, and also for the normalizer we adapted it to all of the training features. So yeah, I think now you learned a lot in this tutorial, how we can download and load CSV data, and how we analyze it and pre-process it with the Pandas framework, and then how we use the normalization layer to normalize our data, and then how we set up a single linear regression model with this dense layer. And then again, training and evaluation is the same like last time. And yeah, and we also learned about the effect of the activation functions in a deep neural network. And yeah, that's it for today. I hope you enjoyed this tutorial, and if you liked it, then please hit the like button and consider subscribing to the channel, and I hope to see you in the next video. Bye! Hey guys, welcome to another TensorFlow tutorial. Today we're going to implement our first convolutional neural net. So a convolutional neural net looks similar to our feed-forward neural net from lesson number 3. The main difference now is that we use convolutional filters instead of just dense layers. So here's a typical architecture of a convnet. We have our input image, and then we apply different convolutional layers with activation functions, like here the ReLU. And we also apply pooling layers to reduce the size of our image. And then at the end, we do classification, and this means that we use a fully connected layer at the end, also known as the dense layer, with an output for each class that we have. So our convolutional layer uses convolutional filters, and the filter slides over the image and then calculates a new value and writes it into the output image. So I will not go into detail here, but I will provide some links if you want to learn more about the theory here. So here's another image of a convolutional filter. So at first we put it at the red position, and then we calculate the convolution and write the output in here, and then we slide it to the next position, so the green one, and do the same, and then we slide it to the blue position and do the same. And this is how we calculate the convolutions. And then we also apply max pooling, which is also just a filter. For example, here a 2x2 filter. And we put it at the first position and calculate just the maximum value, like here the 20, and write it to the output. And then we slide it to the next position and do the same, and so on. So this reduces the size of our image. And this is all the concepts that we're going to apply. So here again is an image of the architecture that we're going to implement. So we have the input image, then we apply convolution plus the ReLU activation function plus pooling. Then we do the same thing again. And at the end we flatten the image to squeeze it into one dimension and use a fully connected dense layer with the softmax activation function, and then do the classification. So this step at the end is the exact same that we used in tutorial number 3. So I recommend that you watch this one first if you haven't already. And now we can jump to the code. So in this example, we're going to use the CIFAR10 dataset. This is an image dataset of 60,000 32 by 32 color images, and we have 10 different classes that we see here. For example, airplane, a car, bird, cat, and so on. And this is what we're going to classify. So now let's jump to the code. Alright, so here I've already written some code. So this is similar to the code in tutorial number 3. So again, we import the things we need, like TensorFlow and Keras and layers. Then I import matplotlib. Then we use the CIFAR10 dataset, which is integrated in Keras datasets, and we can split this into training images and test images. And now if we print the shape, we see, for example, that this is the train images has 50,000 samples, and each image has the size 32 by 32 by 3 because it has 3 color channels. Then we normalize our data, so we want it to be in the range from 0 to 1. Then here I have the different class names, and I've written a helper function to show you some example images. So let's run it up until here. So now if I say Python and then the name of this file, then we see some example images here, and the images are very blurred because our dimensions are very small, but that's okay. So now let's stop this, and now I can remove this code for plotting. So we don't need this anymore. And now here we define our Keras sequential model like the last time. And now this is what we have to implement. And then the code after that is exactly the same as in tutorial number 3. So again, we define our loss and the optimizer. So here we want the sparse categorical cross entropy and say from logits equals true so that it applies the softmax. So this is important here. Then we define some metrics that we want to track. And then we have to call model compile. And after that, we start our training by simply calling model.fit with our training images and training labels. And then we can evaluate it by calling model.evaluate with the test images and the test labels. So yeah, that's the whole code. And now the only thing left to do here is to define our model. So now let's have a look again. So again, we want to apply convolutional layers with an activation function and a pooling layer. And then the same thing again. And at the end, we want to flatten it and apply the fully connected layer. So let's do this. So first, let's add a convolutional layer. So we can do this by saying model.add, and then we use a layer from keras.layers, and then this is the conv2d layer, so a 2D convolutional layer. And now first we have to specify the filters. So this is the number of output filters after this convolution. So here we say 32. Then we have to specify the kernel size. So here let's use a filter kernel of size 3 by 3. Then I also write the strides and padding here for you. So strides equals, let's say 1 and 1. This is just the default, how much we want to slide, how far we want to slide it over the image. And padding equals valid. So you have the option to say valid or same. These are basically two different rules how the padding is applied. So let's say valid here. And then, as I said, we want to use an activation. So we say activation equals relu. And for our first layer, we also specify the input shape. And this is 32 by 32 by 3. And now we have this. So now after that, we want to apply a pooling layer. So we say model.add, and then again layers.max pooling 2D. And then here also we can define the pool size. So here let's just use 2 by 2 as default, or I can again write it for you so that it's clearer. So we use a 2 by 2 max pooling layer. And then we do the same thing again. So let's copy and paste this. And here we remove the input shape, so we don't need this anymore. And let's also remove this because this is just the default. And then here I want to show you that you can specify a value for each dimension, or you can just specify a single integer value, and then it's using this for each dimension. So this is the same as this. And then again another max pooling layer. And now we want to, let's have a look again. Now we want to flatten it and then apply the fully connected layer. So now we add a model.add and then layers.flatten. So we squeeze it into one dimension, and then we say model.add, and we want to add a dense layer. So layers.dense, and then here let's use a hidden size of 64 and also an activation, and here again we use relu. And then let's do the same thing at the end. So model.add a dense layer, and now we have to specify 10 output classes. And here we don't want an activation function because we say from logits equals true for our loss. And now this is all that we need. So this is our first convolutional neural network. And now, for example, we can call print and then print the model.summary. And now, so for now, let's stop here. So I say import sys and sys.exit. So it stops here and then don't start the training. So let's run it again and see if it works. All right, so now this worked. So here it prints the summary, and then again we can inspect our different layers and the output shapes of each layers and the number of parameters that we have for training. So yeah, this is basically an overview of our convolutional neural net. And now we can remove this, and then the same as last time, we compile the model and fit it and evaluate it. So let's run it. So let's clear this and run the training. All right, so training is done and we see that the loss decreased and the accuracy improved with each epoch, and then we have a final evaluation accuracy. So it's not perfect yet, it's only an accuracy of 65%. But we also only trained it for 5 epochs, so I'm sure that this will get better if we train it longer. So yeah, now you see that our ConvNet is working and you know how you define and set up your model. And now you can, for example, play around with the learning rate or play around with different architectures here, and then you can further improve the accuracy. So yeah, I hope you enjoyed this tutorial, and please hit the like button and consider subscribing to the channel, and I hope to see you in the next video. Bye! Hey guys, welcome to the next TensorFlow tutorial. In this episode I want to show you how we can save and load our model. This is very simple with the TensorFlow API, so let's have a look at how we do that. And here I have the same code as in tutorial number 3, where we implement a simple feed-forward neural net and use it for the MNIST dataset. So after we define our model, we compile it and fit it. So we start the training and then we evaluate it. And after that, we want to save our model. And here we have 3 different options, and I want to show you all 3. So we can save and load the whole model. We can save only the weights, or we can save only the architecture. So let's start with the whole model, and this is super simple. So we can just say model.save and then specify a file name. And here we have 2 different possible formats that we can use. So we can use the TensorFlow saved model format, or we can use the HDF5 format. And this depends on the ending that we use. So for example, if we just use NN, so for neural network, a file name without an ending, then it's using this format. And if we specify the ending H5, then it's using this format. So both work fine. In the TensorFlow docs, they recommend to use this format, but I think this one works as well. So you can use both. So let's use both formats here to demonstrate you the difference. So let's use another one, neural, let's call this neural net without an ending. And now if we run this, then it starts the training, and after the training it should save the model in both formats. So let's say Python and then the name of this file. So this is tutorial number 6. All right, so training is done and it saved our model. So we see the H5 file And for the other one, where we simply used neural net, and then it's using the saved model format, and for this it creates a whole folder with the files in it. So both work fine. And then in order to load it, let's use a new model, and we can load this by saying new model equals keras.models.load model, and then the same file name. So let's use nn.h5. And now we have it and can do the same thing. So now if I say new model.evaluate, then this should produce the exact same results. So now we could delete all of this. So I leave this here so that it prints the first evaluation and the second one, so that we can see that this is the same. And here I want to mention that so last time for metrics we just used the name accuracy, and in the current TensorFlow version 2.3 there is a bug. So if you use the string, then after loading with this specific loss, it will not produce the same results. So you should use this Keras metrics object here, and then it works fine, but this will be fixed in the version 2.4. So let's run it, and then we should see the exact same evaluation results for our original model and our loaded model. Alright, so here we have it. So here we have the evaluation of the original model, and then after loading we have this one. So this is exactly the same, and don't worry about this warning. So this appears if we use the saved model format, but I think this is also a bug and should be fixed in the next version. So yeah, I think we see how we can save and load our model. So it's that simple. We only use model.save and then can call Keras models load model again. And then we have the exact same model. So this is how we save the whole model. And now if we want to save only the weights, we can do it very simple as well. So we can say model.save weights, and then let's call this nn.weights.h5. And again, here we have both options, so with an file name ending or without. And then again, if we want to load the weights, then we would have to set up our model like here. And then without training, we can simply say model.loadWeights and then this file name, so nn.weights.h5. So here, again, here we would have to initialize our model. And now as a last option, if we only want to save the architecture, we can get the architecture as a JSON string by saying our JSON string equals, and then we use model to JSON, and this saves the architecture of our model as JSON string. And then, for example, we can save this, so we can say with open and then our file name, so nn model, and we want to open it in write mode, and then sf, and then we say f.write our JSON string, and then the same thing when we load it. So for loading we do the same thing, we say with open and then the same name nn.model, and then here in read mode as f, and then we can say our loaded JSON string equals, and here we say f.read. So we don't need to import the JSON module here. This is already implemented in the TensorFlow API. And then when we have our loaded JSON string, we can set up our model by saying new model equals keras.models.load models.model and then underscore from JSON, and then here the loaded JSON string. And now here, then this will only load the architecture. So if we say print new model.summary, then it would look the same, but here it does not have the weights yet. So then we would still have to train it. But yeah, now you have all the three different options. And I think the first one is the simplest one, but it's also the most expensive one. So sometimes you just want to save the weights or only the architecture. And yeah, so now you know how simple it is with the TensorFlow API. And then you can start saving and loading your model. And yeah, that's it for now. I hope you enjoyed this tutorial. Please hit the like button and consider subscribing to the channel. And I hope to see you in the next video. Bye. Hey guys, welcome to another TensorFlow tutorial. Today I want to show you the functional API. The functional API is another way to define our models and is more flexible than the beginner-friendly sequential API. So I want to show you how we can use the functional API and some reasons when and why we want to do that. And at the end I will walk you through another example with an advanced classification task. So let's start, and here on the official docs they say that the functional API can handle models with nonlinear topology, shared layers, and even multiple inputs or outputs. So let's jump to the code and have a look at what that means. So here is a typical example of the sequential API that you should know by now. So we set that up, and now with the sequential API, we can only have a linear graph, so like this, so one input and then one layer after the other and only one output. And now with the functional API, we have a lot of more options. For example, here at the end, we can have multiple outputs. We can also have multiple inputs. Or somewhere in the middle, we can have different paths. And yeah, so it's more flexible. And now let me show you how we use the functional API. So with the functional API, we start by creating an input layer like this, and then we define our layers. For example, here, this is our typical Keras layer. So we define a flatten layer, a dense layer, and another dense layer. So these are the exact same layers as here. And then we call them. So we start by saying x equals, and then call our first layer with the inputs. And by the way, all these layers are callable like functions. And so now we first call our flattening layer, then we call our first dense layer. So we say dense 1 with the x, and then we assign it to x, and then we say again x equals dense 2, and again we pass in x. And now this is our last layer. So this means that this is our outputs. And then we create a model by saying model equals Keras dot and then a model. And then here we have to define the inputs equals the inputs and the outputs equals the outputs. And we can also give it a name. For example, let's say functional model, and then we have it. So now we can print the model summary like here and run the code. So let's see how that looks. Let me clear this and run it. And then first we print the summary of the first sequential model and then another summary of the functional API model. So we see that they look almost the same. So this is our sequential model. And then here, this looks the same. It has the same number of parameters. The only difference is that we see the input layer, but this doesn't make a difference. So now we see that works. And now again, let's have a look. So for the functional API, we have to define our input. So an input here. And then we pass all the inputs through all the layers. And then we also have to define a output. So this is what comes out in the last layer. And then we define the inputs and the outputs for the model. And then we have it. So this is how we do it. And let's say, for example, we want to have multiple outputs like here. So let's say we have another dense layer. So let's call this dense 2. And this is another keras.layers.dense layer. And let's say, for example, here we only want to have one output. So this is a second binary classification task. And then at this point, so after this dense layer, then our graph goes in one direction using this layer. And then we define our second output. So let's call this outputs 2. And then here we call the dense layer 2. And with the same previous input from here. And then in the outputs, we define a list and use outputs and outputs 2. And then when we run this, then we should see a new model with 2 different outputs. All right, so here we have our new functional model, and we see here at the end we have the first outputs, which is connected to the dense layer, and then we have the second output with only one label, and this is also connected to the dense layer. So this works, and yeah, I think now you should get the concept. So you can do the same thing with multiple inputs. So define another input here and then also pass in a list for the inputs here. So yeah, this is how we set up a model with the functional API. And now let me show you how we can convert from a sequential model to a functional model. So this is very simple because we can iterate over the layers. So first, let's define a new empty sequential model. And then we can say for layer in model.layers, and then we say new model at our layer, like we can add it with the sequential API. And this is all that we have to do. But of course, this only works if the layer graph is linear, like here. So this first option. So then we can easily convert it. And now if we want to do it the other way around, let me copy and paste this here. So first, again, for the functional API, we have to define an input. And then we can access the first layer by calling model layers 0 and then pass in the inputs. And then we again do our for loop and iterate over all the other layers starting at 1. And then we call the layer and give it the input and assign it to this. And then at the end we say our outputs is the output from the last iteration. And then again, we define it here by saying our model equals a Keras model with the inputs and the outputs. So yeah, this is how we convert it. And of course, this is very flexible because here, let's say we want to leave out certain layers. Then, for example, we can do an if statement here, or which is also a very common case is that we leave out the last layer. So here we can only iterate to the second last layer. The very last one is excluded. And then we have our new model like this. So this is very powerful for transfer learning, which is a very important concept that I cover in one of the next videos. And now let me list again some advantages of the functional API. So again, with the functional API, we can have multiple inputs and outputs. Then we can have shared layers, like for example, here in the second case, also with multiple inputs and outputs. So this one is a shared layer that we can use for both ways in our graph. And then we can also extract and reuse the nodes in the graph of layers. So this is again very powerful in transfer learning. And now let me talk about how we can access the inputs and the outputs of a model and the layer. So for every model, we can call model.inputs and model.outputs to get the inputs and the outputs. And we can also, for each layer, get the input and the output. For example, we can say our input 0 equals the input of layers with index 0, and the same with the output. So let's run this and print this. So let's print the inputs and the outputs of the whole model, and let's also print the input and the output of the first layer. So let's clear this and run this. And then we see we have here our input. So this is the same as we're seeing here. And we have the outputs, which is in this case, we have 2 outputs. And then from the first layer, again, we can see the input and the output. So this is how we can do this. And now let me show you how we can use this for transfer learning. For example, we can, so I will cover this in another video in more detail, but for now, let me just show you a quick example. So let's say we have a already trained model. This is our base model. And now we want to modify only the last layer. So we want to cut out the last layer of the base model and use our own. So we can do this by accessing the output of the second last layer like this. And then we define a new output, so a new dense layer, and pass in this last output. And then we set up a new functional model by saying the inputs are our base model.inputs, because we used the same graph, the same input and the same graph up until this point. And then the outputs is the new outputs. So yeah, this is how we set up a model for transfer learning using the functional API. So yeah, I think you should see how flexible this is by now. And now let me show you an example with a classification task where we actually have 2 outputs that we want to predict. So let me go to a Jupyter notebook here. And in this case, what we want to do is, again, I used the MNIST data set. So we want to predict the digit, the handwritten digit. But now let's also assume that we want to predict if the digit was written with a right hand or a left hand. And now let me walk you through how we do that. So again, we import the things we need. Then we define our functional model like this. So we need to define an input, and then let's say we use a flattening layer and a dense layer. So this is the same as in the tutorial number 3. And then in the last layers, we want to get 2 different outputs. So one dense layer with 10 outputs for the 10 different labels. And here we use the activation function softmax, and we give it the name category output. And then we define another dense layer with only one single output. So this should say if it's written by a left-hander or right-hander. And for a binary task, we use the sigmoid function at the end, and we call this left-right output. And then we call all those layers. So we call the first layer with the input, the next layer with the previous output, and then we call the first dense layer and at the end here and say this is our outputs 1 and the other one is our output 2. And then here we define our model with the inputs and the outputs as a list. So now if we print the summary, we can see again we have this architecture, and at the end we have the category output, which is connected to the previous dense layer, and we have the left-right output, which is also connected to this dense 1 layer. So this is our model, and now when we define the loss and the optimizer, now we also need 2 different losses. So we have the sparse categorical cross entropy that we already know. And note that here I say from logits equals false because I already used the softmax activation function here. And then we define a second loss. So in this case, for this binary classification, left or right, we say we use the binary cross entropy, and again we say from logits equals false because we use the sigmoid here already. And then we define our 2, so again we have our optimizer and the matrix, and then we define our 2 losses as a dictionary, and as the key we use the same name as we used for our output layers, so the category output and the left-right output, and then our model knows which belongs to which. So then we can compile our model, and now of course when we want to train our model we need 2 different sets of labels. So we have our labels that we get from the MNIST data. But of course now we also need labels for the left and right prediction. And here I just make a dummy set. So I say that each number that was written, that is larger or greater than 5 was written by a right-hander. So I create a new data set with the same shape as the original data set, and now we only need an integer type and fill it with zeros, and then we iterate over our original training labels, and we say if our y is greater than 5 then we set it to 1. So each digit that is greater than 5 was written by a right-hander. So now we print this, and then again we define our y as a dictionary, and again here with the same keys. So the category output with our original MNIST labels, and then the left-right output with our new dummy labels. So let's run this. And then we see, for example, here we have the digit labels between 0 and 9. And we see for each digit that is greater than 5, we have a 1 here and otherwise a 0. So this is how our new labels look like. And then we pass it in like this. So simply we fit our model with the training data and our new Y data, which is the dictionary then. And then we can start training. All right, and training is done. And then we also see we get a loss for both different losses. So the category output loss and the left-right output loss. And we also get 2 different accuracy metrics. And we see that both are very good. So this one and this one, both are over 98%. And now when we want to predict this, we can simply call model predict with our X test. So our MNIST data still has only 1 input. And then we get 2 different predictions. So we get a list here. So if we print the length of the predictions, then we see this is 2. So now to get the predictions for the category, we have to access index 0 and for the other one index 1. So now here I grab only the first 20 predictions of each output. And then for the label classification, like the last time, we have to use the argmax. So here I already applied the softmax function. And for the left-right prediction, so here we applied the sigmoid at the end. And here we say if the output is greater than 0.5, then we say this is class 1 and otherwise class 0. So let's do this. And then here I print the original test labels, then the predictions for the digits and also the predictions for left or right. So let's have a look at this. And we see these are our original labels and these are our predictions. So I think all of them are correct here, which is very good. And now for every number that is greater than 5, we should see a 1 here. And I think this is almost the case. So here in this one case, we have a wrong prediction, but otherwise it's correct. And yeah, so I know this is only a dummy example, but now you should get the concept how we apply a model for 2 different outputs that we want to predict. And yeah, I think this is very powerful. And I hope you enjoyed this lesson. And if you enjoyed it, please hit the like button and consider subscribing to the channel. And I hope to see you in the next video. Bye. Hey guys, welcome to another TensorFlow tutorial. Today I'll do another full project walkthrough, and I think this project is going to be real fun because we're gonna use a real image dataset from Kaggle with Lego Star Wars minifigures, and we're trying to classify the characters. So along the way we will learn how we download and organize our data and how we load the images into TensorFlow and pre-process them. Then we set up a convolutional neural net, train it and save our model. And along the way, I'll also introduce some new concepts like image augmentation and Keras callbacks. So I hope you stay until the end and we'll find out if we can correctly identify Luke Skywalker. So here is the image data set. It's available on Kaggle and I will put the link in the description. And then you can just click on download and download the data. So I already did this and copied it into my project directory. So here this Lego folder. And we have some different categories like Harry Potter and Jurassic World. But now I'm only going to use the Star Wars figures to make it simpler and easier to follow for you. So let's make a copy of this folder so that we have a backup because we are going to reorganize the data a little bit. So let's rename this to Star Wars Images. And then inside here we have 10 different classes, but right now I'm only going to use the first 5. So again, to make it simpler for you. And now let's have a look at these images. So now in this Star Wars images folder, we have, for example, class 1, this is Yoda. Class 2 is Luke Skywalker. Then we also have R2-D2, then we also have Mace Windu, and as last character we use General Grievous. So these are the characters that we want to identify. And right now the first thing I want to do is to reorganize this folder structure a little bit. So you could load it like this, and you also have some metadata with the information for each directory, so you can load it with this. But I want to make it a little bit simpler so that we can easily load it with the TensorFlow image loader. So I want to separate the data set into training images, validation images, and test images. So we create 3 folders in here, and then in each of the folders we again create images for each character. For example, we have a training folder, and then in the subfolder we have a folder for Yoda, Luke Skywalker, and so on. So this is the first thing we're going to do. So here I'm in a Jupyter notebook, and here we import the things that we need. Then here I named the base directory where we have the imagers, and then I hard-coded the names of each character, so these 5. And I'm also setting a random seed to make it a little bit more reproducible. And now the first thing we want to do is to create our different folders, so we can of course automate this with Python. So now if I run this code and we have a look, then in here it created these 3 new folders, and then inside of each it created a folder for each character that we have. So right now these are empty, and now we are going to take the images from in here and then copy them into here. And so we have about 12 to 14 different images for each character. I know this is not a big amount, especially not for deep learning, but it's enough for this tutorial, and I show you at the end that we get a pretty good accuracy. So now we want to take about 60% for training, then 25% for validation, and the rest for testing, and then copy them into these folders. So if I run this, then it prints the total number of images in each directory, and then the number of training samples, validation samples, and test samples. So now if we go back in here, then each of these folders here are empty. So we can actually delete them. So now move to trash. And now in the training folder, for example, we should have the images. So we have training images for each one, testing images for each one, and validation images for each character. So again, this is what your structure should look like, and this makes it very easy for the TensorFlow image data loader. So now we can go ahead and set up our image data generator. So we can get this from Keras preprocessing.image data generator. And in here you can pass in your own preprocessing function. For example, you can write a function that normalizes the data. But in the special case that we only want to normalize it, we can also pass in the rescale argument. And then here we use 1 divided by 255. So we want to have our images in the range between 0 and 1, like we did in the examples before. And then we have to call this, with this generator, we call the flow from directory function. And then in here we pass in the directory for training. So this is in Lego Star Wars images and then train. And then we can specify the target size. So right now I think the images have the dimension 512 by 512. And we can specify a target size, and TensorFlow automatically does the resizing for us. Then I specify the class mode because I want to have the labels as a single integer value. So you can also, for example, use one hot encoding here. Then you can use the batch size. Then for our training images, we say shuffle equals true. Then we specify that we have RGB images. So again, you can check out the arguments in the documentation. And then we specify the class names that I hard-coded up here. And then we do the same thing for the validation and test images. And the only difference here is that we use, so for training, we use shuffle equals true. And for validation, we say this is false. And so here it doesn't really matter, but especially for testing, you want shuffle equals false. So now if we run this, then TensorFlow automatically loads this for us. So for example, we have, let's print the shapes of the test batch. So we said we only have a batch size of 4. So this is why we have 4 different labels here. And if we have a look at the very first batch, then this is 4 because we have 4 samples, and then each image has the size 256 by 256 by 3, because here we specified this image size and we have 3 color channels. So let's, for example, plot some images with matplotlib. So here, for example, it prints the first 4 images of the test batch. So here we have Yoda and Luke Skywalker. And here we have, we print 4 images of the training batch. So yeah. And now one more thing that I want to show you, what we can very easily do with this image data generator is to use image augmentation. So if we have a look at TensorFlow, then data augmentation is a technique to increase the diversity of your training set by applying random transformations such as image rotation or flipping. So this is very useful to have a better generalization of your model. And we can very easily get this with this data generator. So the only thing we have to pass in here are some more arguments. And then if we want to have this, then we only do this for the training data set. So here, for example, we can specify the rotation range. We can specify a random horizontal flip. And we can also specify a height shift and a width shift, and also shearing and zooming. So now if we use this, so let me apply all these. And then again, you only want to do this for your training data and not for these. And there are several different ways. So of course you can also write your own functions that do this, but this image data generator makes it very simple. So now let's run this again with image augmentation. So let's run this and this one again. And yeah, so here we see, for example, we have a slight rotation and probably also a different zoom factor and maybe some shearing effects here. So yeah, let's run it again. So let's take another random pick from the batches. And again, let's have a look. And yeah, I think you can definitely see that it's doing something with the images. So again, this one is rotated here. So yeah, this is a very nice technique that you can easily apply here. So I'm going to remove this again for now. So because we don't have so many images, and in this case it actually might confuse our model and make the accuracy worse. So in this example I'm going to leave this out, but keep in mind that you can easily do this here. So let's run this and this and this again, and then we should not see the augmentation anymore. So yeah, I think these are the normal images without rotation or any other effects. And now we set up our convolutional model. So this is the same as in tutorial number 5, a simple convolutional neural net with different convolution layers and max pooling and activation functions in between. And then at the end we use a dense layer, and this very last layer is important. So here we are only using 5 outputs because we have 5 different classes. So let's run this and print the summary of our model. So here we can inspect the architecture. And now we set up the loss and the optimizer and the metrics and compile our model. So this is again the same as the last time. So what's important here is to set from logits equals true, because we don't use the activation function here as last layer. So let's compile it. And then we can easily call model fit to train our model. And now here I want to show you another new thing. So I want to talk about Keras callbacks. So with callbacks, a callback is a function that is applied after each training epoch. So here you can, for example, save checkpoints or use different things. And what I want to do here is to use a early stopping callback. So we can very easily use this because this one is implemented in keras.callbacks. And then we say early stopping, and we want to monitor the validation loss and have a patience of 5. And this means that if the validation loss does not improve for the next 5 epochs, then it will automatically do an early stopping of our training. So, and then when we have this, we can specify this argument. So we can say callbacks equals, and then this is a list because we can pass in more callbacks if we want, and then we say early and then stopping, and then we use the rest of the arguments. And now let's train this and see what happens. Alright, so training is done. So we actually said we want to have 30 epochs, but then it stopped after epoch 10 because our validation loss didn't improve. So here we have our lowest value, or here, and then it didn't get better in the next 5 epochs, so that's why it stopped here. And what we can see here is if we have a look at the accuracy of our training data, then here, for example, we have 100 and 97 in the last epoch. So this is very good. But now if we have a look at the validation accuracy, then we see that this one was the best, and then it's actually getting worse. And our validation accuracy is not very good at all. So this is a clear indicator that we have an overfitting problem to our training data. In this case, it's a little bit due to the problem that we don't have so many images available, and especially not very much images for the validation set. So this can be one problem. But yeah, I think in this case, it's very nice to have this callback, and then we can stop and try to improve this model. So I leave this for you as homework. You can, for example, try to use the image augmentation that I showed you, or play around with the learning rate, or also try to change the architecture of our model a little bit. So yeah, this is one thing that we can do. And in the next tutorial, I also show you another very powerful technique with which we can achieve a very high validation accuracy, even on the small data set. So I hope you also watch the next tutorial. So for now, what I also want to do so we can easily save our model. This is one thing I already showed you. So we can save it like this. And then if we have a look at this folder, then it should be here. So yeah, there it is. And then let's plot some data. So here we see the loss, the training loss decreased very nicely, but the validation loss not so much. And the same with the training accuracy. For the training it's very good, but for the validation it isn't. So again, this can be an indicator that we have overfitting here. And yeah, so now let's evaluate it on the test data. And again, here we see that our accuracy is not very good on this test data. And then if we try to do predictions, we call model predict. Then we also have to apply the softmax here because we didn't use it in our model layers as the last layer. And then to get the actual labels, we have to call the argmax along axis 1. So now if we print the actual labels and the predicted labels, then we see we have, it's only 50% correct in this case. So now again, let's print some new images and predictions. So yeah, so here our prediction is Luke Skywalker again. So Luke Skywalker, so this was not very good. So yeah, but now I think you should know how we can apply a full project with a real world image data set. And we even achieved a high accuracy on the training data set with the techniques that we used. But yeah, we still have to improve it so that it's also good on the validation data set and for new data for the test data set. So in the next tutorial, we're going to learn about transfer learning. And with this, I think we will achieve a pretty good accuracy. So I hope to see you in the next video. And if you enjoyed this tutorial, please hit the like button and consider subscribing to the channel. And see you next time. Bye. Hey guys, and welcome to a new TensorFlow tutorial. Today we will continue where we left off last time and apply transfer learning to get a model with a good performance. So I highly recommend that you watch the last tutorial first if you haven't already. And as a quick recap, so we used a dataset from Kaggle with Lego Star Wars minifigures, and we applied our own convolutional neural net. And then we had the problem that for the training, we got a very good accuracy. So this was close to 100%, but it didn't perform well on our validation data set. And also for the final evaluation with the test data set, we only got an accuracy of 40%. So this is not very good. So now what we want to do is we want to apply transfer learning to improve our model. And transfer learning is a very nice, simple, but very powerful technique. So the concept is that we use a model that has been already trained, and this is probably a very good model that with a lot of features and that also has been trained on a lot of data. And now what we do here is, so we take this model and then we only modify the last layers, so we cut them out and then apply our own classification layers at the end and train only these layers at the end. So with this, our training can be very quick, but we can also get the power of the rest of the neural network that is already pre-trained. So this is the whole concept behind transfer learning. And now I show you how we do that with Keras. So the first thing we want to do is to load a pre-trained model. So there are already some models available in Keras, for example, the popular VGG16 model. So you get this by saying TensorFlow, Keras applications, and then the name of our model. So if we download, if we call this, then it's downloading this model and saves it in your folder. So let's run this and print the summary. And here we have the architecture. So you can have a look at that. And now what we want to do here is, as I said, we want to delete the last layer. So you can delete only the very last layer, or you can also delete more and then apply your own. So in this example, we only take out the last layer, so this dense layer, and then apply our own dense layer with 5 different outputs, because in our example, we have 5 different classes. And right now, this is a Keras functional model. So I already talked about the functional API. And if you haven't, then I also recommend to watch this one first, and I will put the link in the description. But I also said that we can easily convert this to a sequential model. So we can do this by setting up a new model and say this is a sequential model. And then we iterate over all the layers except the last one. So this is not included. And say model add layer. So now let's run this and print the summary. And then this should be the same, except that you don't see this layer. So So here, this is the original summary. And here we have this as last layer with 1,000 outputs. And now in our case, this should be the last layer. So let's have a look. And yes, here it is. This is the last layer. And now what we want to do here is we want to set all of those layers to trainable equals false, because we don't have to retrain these again. We only have to train our new classification layer. So we loop over all layers and say layer trainable equals false. And for example, here you see the trainable parameters and the non-trainable parameters. And now if we do this and print the summary again, then we see that now all of our parameters are non-trainable. And now we add a last dense layer. And by default, now this is trainable again. And then again, we set up a loss and a optimizer and compile our model. And then, so last time I told you how we can use this image data generator and then call this .flow from directory function. And this very easily loads the images from a directory, and we can also apply pre-processing and rescaling and even image augmentation here. So last time we applied this rescaling here, and now this time what we want to do, we want to apply the same pre-processing function as in our base model, so in this VGGNet. So, and we also get this by saying this is available in TensorFlow Keras applications, then the name of our model, and then .preprocess input. So this is our preprocessing function. And then we can give this to our image data generator with the argument preprocessing function. So this is the same for our training, validation, and test set. And then we call this flow from directory for each one, and these are the same arguments as last time. And now this is loading the images from the different models. I didn't run this cell, so let's run this and this again. And now we have it. And now again, this is the same as last time. So we fitted our model and we applied this early stopping callback. So if our validation loss does not increase for or improve for 5 epochs, then it does an early stopping. So let's apply this again here. And now let's fit our data. So this is giving an error. You must compile your model before training and testing. So I think I already did this in this cell. So let's run this again and run this and this. And now our training. So now it's working. I guess I didn't run this cell the first time. So now let's see how our transfer learning model is doing. All right, and now our training is done. And again, we had an early stopping. So we see that our accuracy on the test data set is 100%, so perfect. And the validation accuracy is almost 94%. So yeah, I think this is now very good and it's a lot better than last time. And now we specified 30 epochs, but then our validation loss had the lowest value here. And then it didn't get better over the next 5 epochs. So we set patience is 5. And that's why it did the early stopping. So we already had a validation accuracy of 100% in the second epoch. But this might be the case because we don't have so many images available in our validation data set. So I think this result is not very reliable. But yeah, I think we can see how powerful this transfer learning is, because last time we had a problem with overfitting, so that we had a good accuracy on the test, on the training data, but not on the validation data and not on the test data. And now with a transfer learning technique, we can get this after only 2 epochs. And even in this example where we don't have so many images available, this is very good. So now let's evaluate our model on the test data set. And we see in this case, we got 100% on accuracy on the test data. So I guess I'm a little bit lucky this time. But yeah, we see how powerful this technique is again and how simple it is. So you load a pre-trained model and so this one, And then we convert it, in this case, to a sequential model. So you don't have to do this, but this makes it a little bit simpler for you because I know the sequential API is easier to understand. And then we excluded the last layer and added our own dense layer. And then we also set layers trainable to false, except for our last dense layer. And then we did a new training. And as a homework, you can try out other pre-trained nets. So for example, the mobile net version 2 is another very popular net. So you can go to this link, and then here you have all the different available nets. So here's our VGG 16. You also have VGG 19. You have the mobile net and the mobile net version 2 and the ResNet. So yeah, try them out for yourselves. And I can tell you that you might run into a problem when you try to convert your model to a sequential model, because this only works if the architecture of your model is linear. And if you don't know how you do this, if your architecture is not linear, then you can watch my tutorial about the functional API, because there I gave you a tip at the end and showed you how you can still do transfer learning with a functional model. So yeah, check that out and let me know if you can also get an accuracy of 100%. And I hope to see you in the next video then. And if you enjoyed this video, please hit the like button and consider subscribing to the channel. Bye. Hey guys, welcome to another TensorFlow tutorial. Today we'll be learning about recurrent neural nets, or short RNNs. RNNs are a class of neural networks that allow previous outputs to be used as inputs while having hidden states. So this means that we are working with a sequence here. And this is super powerful, and with this, we can use RNNs for many different applications like text generation, text translation, sentiment classification, and many more. So I already have an in-depth tutorial about RNNs where I explain these slides here in more detail. So if you want to learn a little bit more about the theory, then check out at least the first 5 minutes of this video, because now I want to focus on the implementation with TensorFlow. So let's jump directly to the code. So here I already have some code, and this is the exact same code as in tutorial number 3, where we used the MNIST dataset. And then we defined a simple neural net, and then we defined a loss and a optimizer and compiled our model, and then we trained it and evaluated it. So we did digit classification with this data set. And now the only thing we want to change here is to change the model and now use an RNN model. So this is not the typical application for an RNN. A lot of times it's used when we deal with text classification or text generation. But this example should demonstrate that RNNs can indeed be used for an image classification task. And you will see how easily we can create our RNN model with the Keras API. So as I said, when we deal with RNNs, then we deal with a sequence here. And in our case, we have images, but we don't have to change our data set. We simply have to treat our images as a sequence now. So right now, our images have the shape 28 by 28, so 28 times 28 pixels. And now we treat it as a sequence. So this means that we say one time step is one row in our image. And then we also have 28 columns. So this means that our input size is 28 and our sequence length is also 28. So again, this means we have 28 time steps in our sequence, and in each time step we have 28 features. And now when we treat it like this, then we can simply use an RNN now. So now let's go ahead and define our model. So first let's define an empty sequential model. And the first thing I want to do is to add a input. So I say model.add and then Keras and then input, and then here specify the shape, and this is 28 by 28. So again, the first number here is the sequence length, and the second number here is the input size. And now we can add the RNN model. So there are different ones available, and we start with the simple RNN layer. So later I also show you two other famous ones. So for now, let's say model.add, and then we can get this in keras.layers. So we already imported this here. And then we can say layers dot, and now we want a simple RNN model. And now the only thing we have to specify is the number of units, so the number of output units. And this is also the size of the hidden cell. So there are, of course, a lot of more parameters, so I recommend that you check out the documentation for yourselves. So one thing that you should note is that by default, the activation function in an RNN is the TANH function. So let's, in our case, let's try out the ReLU function. And now this is all that we need for the RNN model. So now we have that. And now as we want to do classification, so we have 10 different classes in the MNIST dataset. So then we also, like in the other tutorial, we add a dense layer at the end. So we say layers.dense, and then we want 10 outputs. And this is all we need. So we don't use an activation function here at the end, but then we must be careful and we must specify from logits equals true in our loss function. And now this is all that we need for now. So this is the whole sequential model that we need for a simple RNN. So first let's import sys and say sys.exit so that it runs only until here. So let's run the code until here and print the summary. So let's say Python and then the name of this file. So this one. Oh, and here I missed the equal sign, of course. So shape equals 28 by 28. So again, let's try it. And then here we see our simple RNN has this output shape, and I explain this in a second. And then we have the dense layer with 10 outputs. So let's have another look at the RNNs. So the output shape is n, so the number of samples that we have, and then 128 like we specified here. And what this includes is, so this is a single vector for each sample, and the output that we get is the output of the only of the last cell, the last time step, but this includes all the information about the previous time step. So this is all that we need. So we only need this last cell here. So this is why our output is in this shape, but you can also get an output of the shape, the number of batches times the number of sequences, the number of time steps or the sequence length, and then the number of units. And we get this when we specify there's an additional parameter, and this is called return sequences equals true. So if we use this, by default it's false, and if we use this, then our output is in this shape. And this is, for example, useful when we want to stack multiple RNNs together. So for example, we can use the first one, which will return all the time steps. And then we use a second one where we say this is false. And then here we get this output shape. So again, let's have a look if that's correct. So let's clear this and run this again. And yeah, what I told you was correct. So the first RNN has this output shape because we said return sequences equals true. And the other one has only this output shape. And then again, we have our dense layer. So this might improve the performance of your model. So again, you can play around with stacking of multiple RNNs. So for now, let's just use one, and then let's remove this and then train it and see if it performs well for this classification task. So again, let's clear this and run this. All right, so we see that our accuracy at the end is 97%. So our RNN indeed works well here for this image classification task. And now you know how you can set up your RNN with this simple RNN layer, and you should know how you can treat your input as a sequence. And now I also want to show you two other famous RNNs. So this is only the simple RNN layer, but there's also, for example, the LSTM or the GRU. So both are two popular RNNs as well. They both typically perform a little bit better than the simple RNN, and I think you don't have to change anything else. So the parameters are mostly the same, and also the structure of the outputs is the same. So yeah, play around with this as well and try out the GRU or the LSTM. And yeah, I think that's it for now. And in the next tutorial, we learn how we apply this for a text classification task. So I hope to see you in the next video then. And if you enjoyed this tutorial, please hit the like button and consider subscribing to the channel. And see you next time. Bye. Hey guys, and welcome to another TensorFlow tutorial. In this video, we will learn how to use an RNN for text classification. So last time I gave you a quick overview and showed you how we treat our input as a sequence and then create an RNN model. And now we apply this to a very interesting task, which is text classification from real-world data. So we analyze Twitter tweets and want to predict if the text is about a disaster event or not. So here I'm in a Jupyter notebook and I already imported the things we need. And then the data set we're going to use is available on Kaggle. So I put the link in the description, of course. And this is called the disaster tweets. So we want to predict which tweets are about real disasters and which are not. And there are two files available, so the training and testing CSV, but the testing CSV doesn't include the label. So this is for the submission if you want to participate in this competition. So I only downloaded this train.csv and then put it in my folder already. And then we use pandas to load the data. So we can call pandas read CSV and then the name of the file. And now if we have a look at the shape, then we see we have 7,630 samples and then 5 columns. So now let's have a look at the first 5 rows. So here we see we get some additional information like the ID, the keyword, and the location, which we don't need now. And then we have the text. So this is the actual tweet. And then the target label. So 0 for no disaster and 1 for this is a disaster tweet. So let's also analyze how many of both classes we have. So we have this many which are about an actual disaster and this many which are not about a disaster. So I guess it's pretty much balanced here. I think that's okay. And yeah, so now we can go ahead and want to pre-process this text a little bit before we can use an RNN later. So the first thing I want to do is to clean this data a little bit. And I want to remove URLs because it doesn't give us any information. And I also want to remove punctuation. So for this, I already implemented these helper functions. So this one is using regular expressions. And if you want to learn more about this, then I also have a full guide on my channel that you can check out. And yeah, so now let's define these two functions. And here, for example, these are all the punctuation characters that we want to remove. So now if we have a look at this example, then here it finds one tweet with a URL. And if we remove this, then it has only this format. So now with these two functions, we can simply for our data frame, so our pandas data frame, we can call this map function, and only for this text column. So we say data frame.text.map and then these two functions, and then again we assign it to the text column. So now this means we remove all the URLs and all the punctuation characters. So this is the first pre-processing I want to do. And then I also want to remove stop words. And for this, we're going to use the famous NLTK library. So this is a very popular library in Python for natural language processing. And then you also probably have to say nltk.download. And by the way, you can simply install it with pip. And then here I want to get all the stop words and then remove them. So by definition here, a stop word is a commonly used word such as the, a, an, in that a search engine has been programmed to ignore. So we want to ignore these stop words. So we get all the stop words from NLTK. And then we remove it again with a little helper function. And so let's here print the stop words. So here you see all the different stop words. And then again, we call this map function with this function. And on the text column, so this removes all the stop words. And now let's have a look at some example text. So this is the text column. And now we want to prepare this text so that we can use it for a RNN. So we cannot use it like this with all the strings. So we somehow have to transform this to a representation that our model understands. And for this, the first thing we want to do is count all the different words. And here we want to make use of a very nice object, the counter object, which is available in the collections module in Python. And then we count all the unique words. So we iterate over the text column. And then we say for each text, so basically for each line in this text column, we iterate over each line. And then for each line, we split it. So we get an array of all the different words. And then we iterate over all the words and put it in our counter. And then each time this word appears, we increase the counter by 1. So now if we do this and then return the counter and apply this function for the data frame text column, then we get the counter and we get the length of the counter. So this is the number of unique words. So we see that we have almost 18,000 different words in all these tweets. So let's also have a look at the counter itself. So this is basically looks like a dictionary. So here the keys are the different words, and then we have the count of this word here as a value. So this is how the counter looks. And what's also very nice with this counter object, we can call this most common function. So here we can have a look at the 5 most common words. So we see that the word like is the most common one and appears 345 times. And yeah, then again, let's assign this length of the counter to a variable and call this num unique words. So we need this later. And now I want to split the data set into training and validation set. And for this, I define an integer of, this should be 80% of our whole data we want to use as training, and then the rest of this, so 20% for validation. And then we can use the slicing on the data frame, and then the first 80% of the samples is used for training and the rest for validation. So now we get that. And then we also, so right now we still have the whole data frame. So now we want to split the text and the labels, and we can simply do this by assessing the different columns. So we say train data frame.text.to NumPy, and the same for data frame.target. So we say these are our training sentences and our training labels. And then again, we do the same for the validation set. So if we have a look at both the training sentences shape and the validation sentences shape, then we see that we clearly have more in our training set. And now the next thing we want to do is to apply a tokenizer. So with tokenization, we vectorize a text corpus by turning each text into a sequence of integers. So you will see an example in a second which makes this more clearer. But for now, we want to import this tokenizer from TensorFlow keras.preprocessing.text. And then we create a tokenizer object, and for this we need to give it the number of unique words. So that's why we calculated this earlier. And then we have to call tokenizer.fit on texts and then give it the training sentences, so only the training data here. And now when we did this, we can get this word index. So here each word has a unique index. So let's say word index equals tokenizer.word index, and then have a look at this word index. And then we see each of these words has a unique index. So this is what this tokenizer does. And then we can convert these texts to a sequence. So we can call tokenizer.texts to sequences and then give it the sentences. So don't get confused by this. We have the sentences then. So this is the original text. And then we get a sequence. So this has the same size, but now it has these unique indices. So now we do this for the training set and the validation set. And now here, for example, I compare 5 samples of the training sentences and the corresponding sequences. So let's print this. And this is how it looks like. So now it maybe gets a little bit clearer. So the sentence is the normal text. And then after we applied the tokenization, we get this sequence. So now we have the same length of this array as the text, but now we have an index for each word. So now we have that, and now we want to do one more thing, because right now these sequences can have a different length. So that's what you can see here. But we want to have the same length for every sequence, and for this we apply padding. So again, we import this, we import pad sequences from TensorFlow keras.preprocessing.sequence, and then we have to specify a maximum length. So in this case we say it's 20, but you can play around with more or other ones here. So maybe a tweet might be even longer than 20 different words, so you might increase this a little bit, but then also your training might be longer. So now when we specified this, we can call this function pad sequences, and we call this with the training sequences and our specified max length. And here we say padding and truncating equals post. So this means it just uses zeros. So then we do this for the training and validation sequence. And then if we have a look at the shape here, then we see that they all have the shape 20 in the second dimension, because this is the max length. And now if we print one padded sequence, we see that it used zero padding here. So now again, let's print one sample of our training sentences, one sample of our training sequences, and one sample of the padded sequence, so that you see the difference. And then again, here you see for the sentence, we have all the words. For the sequence, we have these indices, and then for the padded sequence we used zero padding. So now we can check if this is actually correct. So if we can reverse this. So for this we create a dictionary where we flip around the keys and the values in this word index. So if you have a look again, so this is how this word index looks. As key, we have the word, and as value, we have this index. And now we want to store this in another dictionary and do it the other way around. So now we say the key is the index and the word is the value. So this is our reverse dictionary. So let's have a look at that. And then we see all these indices are our keys, and all these words are the values. And now we can define this decode function, which gets a sequence. And then we simply call the get function for each index in the sequence. So this returns the corresponding value. And if it's not available, then it should return a question mark. But so this is if we get new indices, but if we stay in the same training data set, then it should find a corresponding word for each index. So this is the decode function. And then let's try it out. So we call the decode function for one sample of the training sequences. So this one, and then I print the original sequence and the decoded text. And here we see we have this sequence and this decoded sequence. And I think, so we say we have 3 people died heat wave far. So if we have a look at where did I already print it? So here I printed the samples from 10 to 15. So that's the original sentence. So we see that our decoding is correct. So now that we have that, we can come to the actual implementation of the model. So last time I showed you that we can very easily create a simple RNN model or a LSTM model or a GRU model. So in this case, we use an LSTM. So for this, we create first a sequential model. And now since we use text data, we also use this embedding layer. So word embeddings give us a way to use an efficient, dense representation in which similar words have a similar encoding. So if you want to learn more about this, I can recommend this official guide on the TensorFlow website. So here you see that another representation might be one hot encoding, and here we simply use a 0 or a 1. But then there's also this embedding representation. So with this embedding layer, we get this representation, so a dense vector of floating point values. So right now we still have this padded sequence with all the word indices. And now this embedding layer turns these indices into a dense vector of fixed size. So that's why we needed this tokenization first. And now we can use this embedding layer. So this gets the number of unique words, and then a size that you specify, and then also the maximum length that we specified. So this is the input length. And now after we define this, then we can apply our LSTM or RNN layer like the last time, where we only specify the number of output units. And here I also set dropout equals 10%. And then, since we want to classify this, so a 0 or 1 classification, we use a dense layer with only one output at the end. And then we also apply the sigmoid function. So let's do this and print the model summary. So we see after our embedding, we get the output shape of this. So the number of batches, and then the 20 is the maximum length, and the 32 is just the size that we specified here as output size. Then our LSTM has this output shape because we specified 64 output units. And then we have our dense layer. And now, since we use binary classification, we use this binary cross entropy loss. And here we say from logits equals false because we already used the activation function here. And then again, we use a optimizer and define the metrics that we want to track and compile the model. And then we simply train it, so we fit it. And here we want to use the padded sequence and then the corresponding labels and then the epochs. And now this is also new. I think I didn't use this before. So you can, in this fit method, you can use the validation data parameter. And this is a tuple. And here we use the validation padded sequence and the validation label. And now if we do this, then it automatically during training uses a validation data set to do the fine tuning. So this is a nice tip to keep in mind, that you can already automatically do this validation if you specify the validation data here. So now let's train this. All right, and training is done. And as you can see, the final accuracy on the training data is 98%, so pretty good. But for the validation accuracy, we only have 73%. So this might be a sign of overfitting. So this might be a homework for you, that you can further improve or tweak the model a little bit so that this one also gets higher. But as we can see, we did the correct pre-processing with our text data, and we set up a nice LSTM model and then get a very nice accuracy here. So let's do some predictions. So we simply call model predict on the training padded sequence in this case. And as I said, we used the sigmoid function at the end. So we still have to convert this to a label 0 or 1. So we simply say if our predicted output probability is higher than 0.5, then it's 1, and otherwise 0. And now let's print some original training sentences and the corresponding labels and the predictions. So here, yeah, so we see 5 of these are classified as a disaster, and the other one are no disasters. And all of our corrections are correct in this case. So we see, for example, here we have 3 people died, blah blah blah. So this is a disaster. And here Tampa getting flooded, also a disaster. And here at the end we have summer lovely, no disaster. So yeah, it looks good. And yeah, I think we learned a lot in this tutorial. Now you know how to apply some basic natural language processing techniques and then use an LSTM for text classification. And I hope you enjoyed this tutorial. If you liked it, then please hit the like button and consider subscribing to the channel. And then I hope to see you in the next video. Bye.